Last thing we need to deal with. There are 2 more problems we're going to look at in the packet. This is the last type of related rates problem, so please have those packets out. Please turn to problem 14. And I think I want to see if you can draw what is going on here. And this will be the beginning of part 1. There is something different in this one. And I feel like as soon as you read it, hopefully you'll figure that out. I think I need to change the titles for next year so they don't give things away. Read the problem and try to draw a picture. There should be an airplane, a searchlight. I'll get you started. Here's the ground. Okay, let's see. I'm going to put my searchlight over here. I'm going to put my plane over here. It's going west. You did it the other way? Yeah. That's fine. I'm kind of actually assuming half of you probably did it like me and the other half probably put the plane over here going this way. It will work out the same in the end, but if you want to be able to follow, maybe change it so it looks like mine, only so we're on the same page. The numbers will be the same in the end.
No, I just did the searchlight to the right of the plane.
Yes, exactly. So, well, no, I said you probably put the plane over here to the left of the, yes. Okay. It's fine, but if you want to do it my way, it might make it easier to follow. I've got that. I've got a right triangle. Are any sides of the right triangle not changing? The altitude is 4,000 feet. Not degrees. I don't know why I did that. 4,000 feet. It's flying west. I know I'm going to need some variable for this distance down here. I'm going to call it x. Is there anything else I'm going to need to label in here? Normally I would do that, but actually, nothing in this problem involves that. What was that? Aha. Okay, I'm going to call that theta, because that's what we usually use for angles. I am not told anything about the hypotenuse, not a specific amount, not a rate of change of the hypotenuse, so we don't need any variables there. I think I'm good with it labeled the way it is. Nope, we already have the part 1 over there. I need some way to relate x, 4,000, and theta. Perhaps the title will help. Rohith. Tell me more. Tangent. Sure. Right triangle trig stuff is what this is all about. We can say that the tangent of theta equals 4,000 over x. There is another way we could do this. Rather than tangent, we could also use? There's only one other option. Nah, because we don't know anything about the hypotenuse. Cotangent would also work. I'm going to go with tangent, though, because I think that's a little bit more obvious. Okay. We have a rate. The plane is flying west. What does that mean? dx dt equals, now, given the way that I drew my picture, if I'm saying the plane is over here and flying west, is x increasing or decreasing? If my plane is here, oh wait, hold on. Okay, right, my plane is here, west is not that way, west is this way. If it's going west, is x increasing or decreasing? Decreasing. Now, if you initially put the plane over here, because nothing in the problem told me it had to be on this side of the searchlight, if you put it to the left of the searchlight, would going west make your dx dt positive or negative? Okay, new drawing. Don't copy this down, you don't have to. But here's the searchlight. Here's my plane, it's over there. Here's my angle. I'm going to the west. If I'm going west, is x increasing or decreasing? Oh, you can't actually see anything. Here's my plane. I'm going to the west. If I'm going west, is x increasing or decreasing? Increasing. The signs will work out in the end. Okay, here's my plane. I'm going in this direction. Okay. Here's my plane. I'm going to the west. As I'm going to the west, aren't I shrinking this side? That's the point. Okay, next, part 2. What are we looking for? Yeah, the change in theta, I want to find d theta dt. In particular, when? That's our setup. Okay. I want to find d theta dt when x equals 2,000 feet. Part 3. I think we just need to do this entire one together. I want to find the derivative with respect to time of the tangent of theta, and the derivative of the other side. You know, it's going to be a little easier if I rewrite this other side as 4,000 x to the negative 1, so I can just kind of use some power rule stuff there and not have to do quotient rule or any of that. Be careful now. What is the derivative of the tangent of theta? T is our independent variable. Theta is not, x is not, so at the end of all those things, we're still getting our d whatever, dt. The derivative of tangent theta is secant squared theta, but then I have to multiply by the derivative of theta, which is d theta dt. On the other side, I'm going to get negative 4,000, x to the negative 2, dx dt, because again, t is the independent variable. And I think I'm going to clean this up, and I think I'm also going to plug in my negative 500, because I can, because that's a rate that's not changing. And I've got secant squared theta, d theta dt equals, let's see, 20, 1, 2, 3, 4, 5, 2, 3, 4, 5. I think that's looking like 2 million over x squared. I think. Yeah. What did I do? Question?
Why is it 4,000 negative?
Because I'm using power rule on this thing. I'm pulling down the power, 4,000 times negative 1, subtracting 1 from the power. Other things. I'm going to go plug in. Part 4, what's the problem? But before we do this, I feel like there are questions that you're not asking. What do we have to talk about before I get on to part 4? Marissa, you've got a question. I know you do.
No, I'm just trying to figure out like independent variable and all that stuff.
Okay.
But I think we just need
Everything is based on time. Technically, this problem isn't really the tangent of theta. It's really the tangent of theta of t equals 4,000 over x of t. Everything is based on time. I'm just not actually showing that every time because it's kind of implied that everything's a function of time. We're treating everything like the y on the quiz you just took where everything's a function of x. Same idea here, everything's a function of time. Other questions?
Even x is a function of time?
Yes. The only thing that wouldn't be is t itself if you ever had a t in these, which we don't. Everything is based on time. Everything's changing based on time. Next, we're ready to plug in. Does anyone have a problem going to plug in right now? Okay. You can certainly plug in your x, but we have that theta. Okay. Here's the deal, though. I actually don't need to know what theta is. I need to know what the secant of theta is. Let me draw up my specific triangle. Okay, so before I plug in, I've got my triangle for my specific instance. I know that here's my theta. I know this is 4,000, and I know at my specific instant that's 2,000. Can you go find the hypotenuse and just leave a root in there? It'll just be big and unpleasant, but whatever. Believe it or not, when we're done, we're going to actually have nice, reasonable, small numbers. But they're airplanes, so we kind of need like big numbers for heights and speeds. And what's that hypotenuse? Square root of what?
1 million.
I'm thinking, 20 million. 20 and then 6 zeros. So really 2 followed by 7 zeros. Maybe. Possibly. I told you a moment ago, I don't actually care what theta is. I just care what the secant of theta is. You can find theta by using inverse trig. Oftentimes, these questions show up as non-calculator things, and inverse trig without a calculator is basically impossible. We don't care about theta, we care about the secant of theta. Secant of theta, how do you define secant of theta from a right triangle? Okay, sure, 1 over cosine. What's cosine in terms of like adjacent, hypotenuse, opposite? Adjacent over hypotenuse. So secant is what? So what is that here? What's our hypotenuse? Root 20 million over adjacent 2,000. You know what though? I don't even care about secant of theta. What do I have in the problem? Secant squared, and actually that's going to be really nice because that'll get rid of my square root. My secant squared of theta is 20 million over 4 million. What is secant squared of theta? That's more reasonable. You're never actually going to have to find your theta. We're going to just have to find a trig function of our theta for our specific instance, and then I can plug things in. So, now I think I have everything I need. Let me just rewrite that problem over here. I had secant squared of theta, d theta dt, equals 2 million over x squared. I know secant squared of theta is 5, so I'm going to say 5 d theta dt. I know that x is 2,000, so I'm going to say 2 million over 2,000 squared. They're big numbers, but whatever. Go work with them. Use the calculator if you need to. And then I just have to talk with you guys about the units. I promise it's going to be a pretty nice final answer. Like a fraction, but a good fraction. Thinking 5 d theta dt just equals a half. So d theta dt is just 1/10. I'm doing 2 million over 4 million. No, I'm not done. 1/10, and we're almost there. Before I finish this off, what do I need to go back and fix for any of you? Last thing we need to do, the units on this. I've made a comment in this class several times to you about trig. How do we deal with trig in calculus? Radians. Our units are going to be radians for the theta. Time should be easy. Per seconds, because that was our other time unit given in our dx dt. Your final answer is 1/10 of a radian per second. To make sense out of that, you might want to convert the radians to degrees. But no, we're going to leave our answer just like this as radians. Nicole?
And the RAD, that's what you want us to use for the abbreviation?
That would be okay. Certainly not just R. R is not really an abbreviation for radians. And if you're not sure, write out the word radian. That's okay. Questions with this? I need to show you one more that's going to work in a similar way. And then please, with the homework, use these two as models for how to deal with these things. I want you to read the next one and try to draw a picture. And you know what? Maybe try to do all of parts 1 and 2. Draw the picture, get your formula. Number 15, last one. Oh, good, another falling ladder. I told you they make good related rate problems.
I found out that actually did happen to my uncle.
Is he okay?
Oh yeah, he was.
Oh, he wasn't. He was just watching it happen.
No, he was on it.
Of-
But like he's fine.
Yesterday I saw a video online of someone falling off ladders and slipped from under.
And you thought of related rates?
Exactly, honestly. I
Wonderful.
would show you the video, but I can't put it in my phone class. So.
That's probably a good thing. Go draw a picture and see what you can do in parts 1 and 2 of this one. By the way, this is my wall. Whatever. Here's my floor. Here's my ladder. Okay, here's the wall. It doesn't count. What?
It's a thick wall.
Well, yeah. I don't know. Where? Does it matter where I put theta? Which one is it? This one or this one? Yeah, between the wall and the ladder. Okay, so that one has to be theta. And I feel like I don't have to label both sides. Because the angle the ladder forms with the wall. This angle over here is not with the wall. That's the key. Ladder, wall. Perfect. Do I need to, which side do I not need to label? The height or the bottom? The height. We're told how the base is getting pulled out. We know something about that, so I know that's going to have to be a variable. I don't need to deal with the other one. Oh, actually, this is going to be easier than the last one. What is it? What are you going to use? Sine. Okay, so the sine of theta equals x over 50. What else do you know? Okay. That's 1/4 radians per second. I'm going to go on. Part 2, we're looking for what? Dx dt. When x equals 25 feet. Before we go on, am I going to have to go and use quotient rule on this right side? How can I get around it? Say that again? We could, but I also feel like I can just write this another way on that side, the right side. 1/50th x. Couldn't then I just use like constant multiplier stuff and not have to do the whole messy quotient rule that I might get wrong? Can't we just say sine theta equals 1/50th times x? Go do your derivative. This is going to be actually a lot nicer than the last problem. Something really nice is going to happen. Remember when you're doing this, though, everything's a function of time, so you're going to get your d whatevers, dt's. So what's the derivative of the sine of theta? You want to say anything else? D theta dt. Be careful. T is our variable. Everything else is based on t. Here's where I think this gets kind of nice, but we still have to be a little careful. What's the derivative of 1/50th x? 1/50 dx dt. Which is nice, which means I don't even need to plug in an x anywhere. I just have my theta. I don't even really care about that. I have my cosine theta, which I'll deal with in a moment. I'm going to go and fill in my d theta dt just because I can. And I'm going to say 1/4 cosine theta equals 1/50th dx dt. That's my formula I'm working with. One more part. Part 4. I need to plug in. Again, I don't care about theta. I care about the cosine of theta. So I'm going to draw out my specific triangle. And because we can, let's go for some exact answers here. Find your height. Let's get a root for that. And you know what, just for fun, let's simplify the root, because we can. And it'll make it prettier in the end. Yes. It'll make it nicer. Why not? Think it should be the square root of 1875 for that side, right? Pythagorean theorem. Let me know when you have something simplified. Oh, and I should have my theta in here.
I'm confused why we need to find that otherwise.
Okay, because I'm going to have to figure out the cosine of my angle. Well, cosine is adjacent over the hypotenuse, so I need my adjacent to my theta. That's why.
I think you can really just figure out theta by doing.
Again, though, oftentimes when these show up on the AP exam, it's not in calculator. So inverse trig without a calculator, I'm not sure how you're going to do that.
Or,
Plus, what was that?
Or the other thing doesn't work at kind of
Yes, don't expect that.
Okay.
Don't expect that. Yeah, what do you know? Okay, what is that side? Yeah, so maybe it is a 30, 60, 90 right triangle. But we don't even really need that so much. What is the cosine of theta? I think it's 25 root 3 over 50. But we can also just call it root 3 over 2. Finish this off. Let's get our dx dt. Let's try to make this exact. And put units on it. .25 root 3 over 4, I think. Radians per second. This is not d theta dt. This is dx dt. So that's the rate of change of that distance that was measured in feet. So we need to say feet per second. For every related rates question on the test, the units are worth 1 point. So we just have to make sure we're good there. Just kind of keep going back to what it actually stood for in the beginning. And those are related rates. The homework will be, I think, a few random related rate things from the book with the similar triangles or the Pythagorean theorem stuff. I didn't like how the book did the angle problems. They made them more complicated than they needed to be, so you're going to get a worksheet with those. And the people on the field trip can find the worksheet on the website. And then the 2.5 worksheet, the implicit stuff, and all that. And you're also going to work on starting that review packet, because our test is when? Tuesday. Review day Monday on all related rate stuff, and test Tuesday. And we're going to shut this off now.